how do you compute the hyperstatic actions which are coming from post tensioning? So, this is a simple equivalent frame of a flat slab that what you are seeing here. For example, here you have a drop panel, right, and here you have a drop panel with a capital, and then you have column above and column below, which are typically assumed to be fixed. Now, you have some loading, and this is a pre-stressing cable profile that what we have, right. Now, when you apply this pre-stress, now this is not a statically determinate system. So, there are columns that are connected at all the supports. So, you are going to develop some moments at these joints. For example, in joint 1, I have MT1 and MB1 is the top and bottom moments that are developing at the locations of this joint. Similarly, at joint 2, and these are the reaction that I am developing, right, while you do the pre-stress, and this is at the nth joint. So, Rn, and then the moment at the top is Mtn from the column above, and Mbn is a moment that is coming from the column below. So, these are the reactions that are developed due to the post tensioning. Now, to find out the hyperstatic at a particular section, if you look at it, let us say this is your joint 1, this is joint I, and then this is the section that at which I am trying to calculate, right. So, if you see here, the hyperstatic moment will be the summation of all the joint moments at the top and bottom plus the reactions coming from each support multiplied by the distances of the reactions from the section where I am considering. So, you sum all of them, that is how you get your hyperstatic moment, right. So, in this way you can calculate your hyperstatic moment. Okay. Now, what are the analysis assumptions that we are making to arrive at the displacement and design values? Okay. So, the stiffness and member properties in analysis are, because typically post tensioning you do and you make sure that you are going to have adequate amount of pre-stress. Under service stress or under service stage, we make sure that it is not going to be cracked. So, for our analysis we use the gross sectional properties, because under service conditions anyway pre-stress members are assumed to be uncracked. So, there are no loss in stiffness due to cracking. So, when you do your modeling in your any of your commercial packages, you do not need to put section modifiers while you calculate your internal forces, at least from pre-stressing point of view, right. Of course, when you do for ultimate, though we do elastic analysis in ultimate, but we consider nonlinearity in the material properties, that will yield to conservative design. But when you do analysis, your section properties does not to be reduced. And we are also going to assume force displacement relationships based on the linear elastic behavior. So, the design values that whatever you are getting from your analysis, moment and shear are based on the cross section properties, right. So, basically we are not going to consider the cracking while we do the analysis to find out the internal forces. Also, when we are designing, also based on the service condition, at service it is assumed to be uncracked. Okay. Now, what are the idealized tendon profile for two span, for example, PT slab that I am doing? One span is having an uniformly distributed load, another span is having a, let us say, a point load. This is we are talking about a two span PT slab, one way system, right. So, what we are saying here is, for this one, of course, because it is subjected to uniformly distributed load, I am going to put a parabolic cable. We know that the drape is basically, if I draw a line like this, it is connecting like this. So, this is your drape of the cable. Now, at mid span you have an eccentricity E1 and this location you have E2. So, the drape is going to be E1 plus E2 by 2, right. Now, we know that the balanced load W is going to be the moment that is created by the drape, which is P into E, P into drape, multiplied by 8 by L1 square, or in other words W1 into L1 square by 8 should be equal to P into total drape, right. So, this is your moment that is created, that has to be balanced by the uniformly distributed load. So, we have also found that expression for that. So, we can find the total slope change between the 2 points of this cable profile. Then we can divide by the length and the amount of pre-stress to get your W1 also. So, that is how we found the vertical component of the pre-stress is proportional to the slope change that is happening per unit length, right. So, in that way also we can derive that. We have done it previously in the load balancing module. Now, the second span we have drape is going to be, for example, if this positive location, if it is E3, my total drape is going to be E3 plus E2 by 2. So, balanced load W2 is going to be basically P into total drape into 4 by L2, or in other words P into drape should be equal to W2 into L2 by 4. So, I can calculate what is W2, right. So, okay. So, here if you see, the center of gravity of the concrete and the center of gravity of the tendon are coinciding at the end of the member. So, there is no equivalent load moments are applied at the end of the member, right. This is just how do we arrive at the amount of pre-stressing for different spans. So, of course, now when you have two things, what is the P that you will choose? You have to choose a P higher value, again also depends upon how much that you want to balance that external load. So, you can take a call. For uniformly distributed load, then it's relatively easy. Even there also, depending upon the span, it will change. So, that is the reason we said we try to at least balance 80% to 100% of dead load. But if you have huge point load, then you have to, as a designer, you have to take a call how much really you want to balance that applied load. Right. This is another example. You have a 2-span system with a cantilever, hanging cantilever. Again, for this one also we can see that we can calculate P into E1 will be equal to W1 into L1 square by 2. So, that will give me what is the W1 that it is acting for this span. Similarly, W2 will be equal to your drape. This is your drape. Now, we can calculate the drape as E1 plus E3 by 2 plus E2, that should be equal to W2 into L2 square by 8. For the span, thus 3, that the drape is going to be E3 by 2 plus E4, and P into E should be equal to your W3 into L3 square by 8. Now, P and E for creating decide. So, now from all these things you get your P, and depending upon how much in each span that you want to balance, you select a higher value of P, so that in all the spans you will be at least able to balance the desired amount of your dead load. Okay. So, previously we have seen, in this case, previously if you see, we have taken a very idealized cable profile with a very sharp change in your cables like this. You see, there is a sharp change, there is a sharp change here, right, at all the support locations, right, but we cannot achieve that in the field. So, typically you put a reverse parabola like this. Okay. This is a parabola and this is a reverse parabola. So, there is going to be a point of inflection that is happening close to the support region, right. So, the code typically gives you dimensions where the length of the parabola from the maximum point to this, we typically take it as 5% of your length on either side. So, this is right 0.05 L and this is also we take 0.05 L. Typically, I mean that numbers can change also depending upon the loading profile that you have. And that is the reason if you see here in the midspan region the loads are all upward, but in the support region because there is a reverse parabola the load is going to push below, but that will go to the column. But what we are interested is in creating that upward load in the majority of the span. So, that is the reason this reverse parabola typically is taken as 5% of the span. So, it is not going to be far away from the support. So, pretty much the entire length 90% of the span will have upward load that it is coming, right. Now, what are the criteria for span combinations, right? We have seen for a continuous system typically interior moment will be high and your span moment, positive moment will be higher at the end span. Now, if I change the proportions of your end span and interior span, then I can achieve more or less uniform values of your bending moment, because please note that here in PT I am using the same cable which is moving throughout the entire length of the slab, right. So, I can come up with a more economical design if I am careful about the span layouts. Okay. So, for example, we typically try to keep internal spans as much as nearly equal, right. The second is the external span, typically we try to keep 0.8 times the length of the internal span, just to make sure that the positive moment on the external span is not going to be very high, and the cantilevers are typically not kept more than 0.3 times the length of the adjacent span, right. And expansion joints, typically, we need to provide expansion joints unless you form that with double column. Now, when you have a irregular layout, then to avoid torsion, typically we create this double columns and put expansion joints, so that torsion is avoided in the design, right. So, if you do that, typically expansion joints should be approximately in the quarter span locations, L4 locations, it is there, that is where your negative bending moment will change to positive moment. These are the typically the point of inflections from bending moment diagram point of view, right. Now, the size of the slabs, again, between the expansion joints should be kept at about 30 meters. You do not go more than 30 meters. So, every 30 meters, otherwise, you will have shrinkage and other things will also start controlling. So, we will try to keep the size or the length of the slabs between the expansion joints to be limited to maximum of about 30 meters. Right. Now, let us look at what are the design steps. Now, sizing, as I have told you, the first thing is to size the depth of the member and allow for the maximum eccentricity of the cable. Now, the maximum eccentricity of the cable will depend upon how much cover is permitted for the reinforcement and tendons. That will again depend upon the exposure condition and the fire requirement according to the code of practice, right. So, then you will have loadings, you have to take care of the loadings, then you need to choose a particular structural system. Again, the structural system, what I mean is, whether you for a particular slab panel, can you convert it into a two-way slab system into one-way slab system, right. If you can do that, finally at the end of the day you have to look at multiple options and then take a call, right. So, but typically from commercial buildings point of view, when you are going for a two-way slab, they go for a two-way slabs with PT layout in both the directions. They do not really explicitly try to convert the two-way slab system one-way slab system. But if it is an RC slab, then it is worthwhile converting a two-way slab into a one-way slab, then you save lot of concrete material in your design. So, that is the point. Then you go for analysis and then you get your design. Now, sizing, when we said, again, we are going to fix the span and thicknesses, what kind of span layout we need to go ahead, that we discussed in the previous slide. Again, cover to rebar and tendons, as we discussed, it depends upon the corrosion, the wear and tear that it is possible, and then from the fire considerations, right. So, this again slab, we said 125 mm is minimum for fire requirement point of view. Then loading, you have dead load, live load and pre-stressing. While you do apply pre-stress, of course, hyperstatic moments have to be considered, right. And also we need to know how much balancing that we are trying to achieve, okay. Balancing of dead load, that is also important. Typically, it is about 100% is what we try to balance, right. So, now let us look at it. Now, structural system, again, as I have told you, one way or two way, I can go ahead, that again depends upon your B by A ratio that we have seen, right. Between 1.4 and 2, you can go for a slab band system with one-way slab. If it is less than 1.4, you can go for a two-way slab, right. And then how do you model the pre-stressings also. Now, when it comes to analysis, we have already discussed, we are going to do elastic theory, we are going to use cross sections, and either you can do a simple frame or you can do an equivalent frame, or if the geometry of the slab is very complex, then I can go ahead and do a finite element analysis. But even if you do finite element analysis, approximately, if you can develop a simple spreadsheet, I can do simple equivalent frame method to verify what results that finite element analysis will give. Most of the time, finite element analysis may give you erroneous results if you are not careful in your modeling. So, always good engineers should always check the results of your finite element analysis with some hand calculations. So, that is why the equivalent frame method that we are going to discuss in the next module will help you to appreciate, and we will find that the hand calculations will give you somewhat conservative results, but they are not going to be very different than what the detailed finite element analysis will give. Okay. From design point of view, again we have already discussed, we have to design the amount of pre-stressing from crack control and deflection control and stress limits point of view. If safety or strength is not meeting, then we can add passive reinforcement. Passive reinforcement is nothing but your regular TMT rebars, right. So, this is the way that overall design process is there. Now, if you are looking at a non-pre-stressed beam, for example, you have a two-span system here, right. For a particular load, what we are really looking at it is, we are coming up with the depth and breadth, and we are also looking at where I am going to put this steel. We are just looking at what is the amount of steel AS, and also wherever the bending moment is there, that is where we are going to put. So, we know, if we know the bending moment diagram, and we can put where the steel that is required. So, we are looking at only the amount of rebar and leaving out the cover from your durability and fire consideration point of view. But here you can see that the same cable, right, the same cable, it is going from one end to another. So, what is that design we are looking at? This cable, how much is the force that is required, or indirectly what is the AP, right, that is what the force is. Typically, initial pre-stressing force FPI, we know that it is basically 0.75 times FPK times AP, right. So, this is fixed because FPK is, as you know, it is 1860 megapascal. So, from here we are looking at basically what is the amount of pre-stressing steel, right. In addition to that, we are also looking at what is the profile of the cable, right. The profile of the cable will keep changing depending upon the loading that you are going to see. That is the reason you see here you have a cable profile with the eccentricity above the CG, right. At mid-span location, here you have below the CG, right. So, in pre-stressing design, it is not only about the amount of pre-stressing steel, unlike RC design. Here also we are looking at what should be the cable profile, right. If at this location, when I look at it, if my bending moment demand is higher, then I can always substitute with TMT rebar to meet my strength requirement. Strength requirement I can achieve, but pre-stressing cable and the layout is coming only from serviceability design point of view, to make sure that you have adequate pre-stressing to tackle the deflection and adequate pre-stressing to make sure that the element is not going to be cracked under service stage, right. So, we have done that. So, now how do we ensure all these things? So, the important factor is the average pre-compression, right. So, pre-stressing cable, right, if I have a cable like this, you know that we always have eccentricity, right. So, when it is like this, so we model that as basically a concentric force plus a moment which is MP, which is P into E, and this is your P, right. So, there is going to be a pre-compression which is P by A, and there is going to be a bending moment which is MP by Z, which is the stress is going to vary. So, this is going to be total stress, and this is your average stress at the centroid location, right. So, the important factor is the amount of pre-compression, that how much you should choose for, right. So, the code gives you a guideline. For example, ACA 318, it tells you the minimum compression force in a PT slab should be at least 0.85 megapascal, the average compression, right, 0.85 megapascal. Optimum value should be at least 1 megapascal. For roof, which are very sensitive to the rain, and if you are in a very cold climate, you may also have snow. So, the water tightness is important. So, if you want a very watertight slab in the roof, then you can go for a high pre-stress of 1.4 megapascal. It relies partly on the structural slab, right. And the upper values are, you never go more than 2 megapascal for slabs and 2.5 megapascal for beams. So, average pre-compression you never go more than 2 megapascal, right. And higher values, sometimes though they may be permissible by the code, they typically do not yield economical design. So, we have to be careful, because when you put excess pre-stress, you may create excessive camber and you may have issues. So, then again you will have again creep effects, it will keep coming, and then you will have cracking at the locations where you do not want. Right. So, that is again sometime in pre-stress, the stage or the loading is also important. So, because I have created an opposite effect, we should also receive the loads in time, so that it is going to relieve some of the excessive stress that you have locked in due to pre-stress, right. So, that is also you have to keep in mind. So, other effects such as on the slab and attached structural members should also be considered. For example, if you have while you do the pre-stress, let us say you have a shear wall that is there in the middle, then that will also produce some restraint, and because of that you will develop some hyperstatic effects, that all those things have to be considered in your design. Right. So, this is another example, what are the profile for beams and distributed tendons, and as you can see here. So, usually we have seen mid span 0.6, and this is your span by 5 this location, the reverse parabola you can see here. This is for exterior span with stressing and exterior span with no stressing, and these are all your controlling points, and you can say these are your low point, and this is your span L2, and this is your exterior span L1, and this is your exterior span again L3, and as you can see sometimes you can also put additional cables by having some intermediate anchors. Okay. For example, let us say if this L2 is very large than L1, then only for this location I can add some additional cables as well, but you have to plan it well, right. So, and again as we have said, this A location, the reverse parabola, typically it is 0.05 times L. Okay. So, in either location, this if you look at it, this and this will be 0.05 times L1, and this will be 0.05 times L2, right. So, in this way this is where you choose your reverse parabola, and these are the point of inflection, right. So, and again as we said, L1 exterior span we will try to approximately keep it as 0.8 times L2, right. So, all these things that we have discussed. Okay. So, and when you put additional tendons, of course, the tendons have to be staggered at every 300 mm. You cannot terminate all the tendons at one location. So, you have to do it in a very staggered manner, right. And these are some of the examples that you can see. This system that you see, this is for one of the raft slabs. You see here you create a very high eccentricity for the cable, and they are all grouped together. In addition to that, you see there is a huge amount of non pre-stressed steel. Huge amount of non pre-stressed steel, because you should always satisfy minimum amount of steel. So, this is from minimum steel requirement. So, that is why in addition to the PT you should also put some bonded steel, right. And here you can see the distribution of the tendon. Again you can clearly see a banded tendons that are going like this, and this side you have a more uniform strands. Okay. These are all uniform, this is banded, right. This is again in a raft slab, you can see. Okay. Now, in a typical RC system, to come up with an economic design, we allow some moment redistribution, because we always, the code asks you to design only an under reinforced section. So, under reinforcement section will undergo a lot of rotation before it can fail. So, it has lot of curvature ductility. So, the same way PT also, if you design it properly, PT systems also will be behaving in an under reinforced or a tension controlled failure mode. That means before concrete reaches its failure strength, the pre-stressing steel will start yielding, right. So, if you do such very good design, so we can also allow for some moment redistribution, right. So, that is what you say. The required ductility in the design of concrete section leads to redistribution of the moment. So, the ductility will come from under reinforced failure mode. So, what is the meaning of under reinforced failure? Again, steel has to yield before concrete reaching its failure strength, right. So, when the section is behaving in a tension controlled or under reinforced mode, the onset of plasticity will lead to formation of plastic hinges, and usually plastic hinges will form at the locations of the maximum moment. Okay. For example, these are all the locations where you can have plastic moment that is possible. These are midspan locations, these are support locations, these are midspan location, right. And for a slab or beam with 0 support width, again these are all the locations where you will have plastification is possible or the hinge locations can form. So, we can definitely here also for a PT system we can allow redistribution of moment, and that can lead to more economical designs provided you satisfy the reinforcement limits. So, what are those? So, does the moment redistribution really make sense for PT floors? Most of the codes like including ACI, they permit elastically calculated moments to be lowered or raised at each hinge location by up to 20%. So, either again I reduce or I can increase it by about 20%. So, then the moment diagram has to be adjusted to accommodate the change, right. So, this is your elastic moment, either it can go up or it can go down by 20%. That is what we are saying. So, this is an equal offset, right. When you offset that entire moment diagram accordingly. So, if I am reducing the negative moment, the positive moment value will go by same magnitude, right. And these are the regions of limited classifications of the supports. So, you can see here at these continuous regions, beam slab regions, though you design it, I think we need to make sure that it is going to form the plastic hinge in a proper way. Okay. So, there is again a moment redistribution is what we are saying. So, this is the moment profile that I have, and this is for you have designed the PT cable. Again, PT cable will always follow bending moment diagram, right. So, we got that, and then you have some continuous reinforcement for this, for negative moments are 2m and positive moments are let us say m. Then you put 2 times the steel and 1 time the steel here, right. So, in a PT cable, but it is the same area of the cable that it is going. So, we want to make sure that this demand, because the cable is same capacity is there. This is for the lower bound and the upper bound. So, I can move it to make sure, because that is what we are saying, this capacity is Mn, here also it will be Mn, here also it will be Mn, provided the eccentricity of the cable is nearly same, right. So, here everywhere the capacity, for example, this blue color is your capacity curve, right. So, you can put it here. So, this is your this is your demand curve, and this is your capacity curve. So, at support location this is the capacity, this is also at the positive moment this is the capacity. So, in both the locations we need to satisfy the same Mn, because the area of the cable is same, because I cannot, unless I put some intermediate anchors and change the number of cable, and if our spans are nearly same, I run the same cable from one end to another. So, the capacity across all the locations will be nearly same, provided again the eccentricity is also nearly same, right. So, this is the problem. So, this way in RC, because the amount of reinforcement is going to change depending upon the location, redistribution is relatively easy. Here it is somewhat more involved we have to do, right. Now, stress check and control of cracking. So, you can see here ACI recommendations are, this is the minimum amount of bonded non-pre-stressed reinforcement that is required. In beams and one-way slabs, bonded steel requirement is not there. For unbonded, when you have a bonded system, there is you don't need to have an extra non-prestressed rebar. So, there is no requirement for TMT rebar. So, when you say non-prestressed rebar, we are talking about TMT rebars that we typically use, which are passive rebars, right. So, when you go for a bonded PT system, either it is a beam and one way slab or flat plate, I do not need to have extra TMT rebar provided that provided PT cable is satisfying the minimum requirement. But when I have an unbonded system which is not bonded to the concrete, the code is saying that for beams and one way slab, I need to have at least 0.4% of area. Similarly, for flat plate, it is 0.075% of H into L, right, HL, 0.75 times HL. H is the depth of the slab and L is your length of the slab. So, this is here. So, similarly, for positive moment regions, you can see here that this is depending upon the amount of compression that you have, NC by 0.5 F5, right. L is the span in the direction of the reinforcement, NC is the tensile force in the concrete under live and dead loads, and A is the area of the cross section subjected to tensile stresses. These are some of the ACA recommendations for minimum amount of bonded non-prestressed steel. So, basically this is TMT rebar, right, our regular TMT rebar. Okay. So, this is the distribution of your bonded top reinforcement in the slab at the interior column. So, you need to put at the interior location, for example, this much steel I have to put, on both sides. Okay. You have both sides, I have to put this. So, this equation, let us assume this is a, let us say, flat plate, and how much is on these both sides? It is basically 0.0075, this is a percentage, right, times HL, and this side also 0.000075 times H into, let us say this is L1 and this is L2. This is the amount of reinforcement that I need to provide on the negative moment region as per ACI, right. So, we need to make sure that the problem with unbonded system, as if for some reasons the cable force is lost, is like a rubber band which is not in contact with water. So, once you cut a rubber band, what will happen? It will go back to its original position. So, you lose the prestress. So, that is the reason for an unbonded system, the code wants you to be more careful and ensure that even in the worst case scenario on the failure of an unbonded system, the regions of critical stress region should have at least some minimum bonded non-prestressed TMT rebars to ensure that it is not going to have an abrupt failure because of loss of prestress, right. Okay. So, what the code recommends is it limits your tensile stresses to 0.5 square root of F prime C, and also it makes sure that you have to provide minimum bonded non-prestressed rebar, or is also TMT rebars, okay, right. So, there is one more thing that we need to consider when we are going for a PT slab design. For example, if you look at it here, this is a regions where non-prestressed regions in a two-way slab with highly concentrated tendon. That means these are all, you see, these are all banded tendons. So, when you have a banded tendons, there is a tendency that you may leave out a region close to the banded region which will not be prestressed. So, the code wants, so this is a region that can develop lot of tensile stresses and it can lead to cracking and failure, because it takes some distance for the prestress effect to be felt. So, there will be region just adjacent to this banded cables which will not see the effect of prestressing, right. Now, that is what the cable is showing. So, the figure illustrates 100% of the tendons in one direction passing through the columns. You see there are edge zones which are not prestressed for the spreading of the compressive stress from anchorage region, because the way that prestressing is spreading out, there are regions which are not prestressed. So, we need to be careful. So, in these zones, bonded reinforcement should be placed perpendicular to the free edge, right. How much it should be? That is the amount that it is giving, 0.0015 minus 0.5 into rho P or PP. What is PS? PS is the reinforcement ratio based on the average effective depth measured to the non-prestressed steel. This amount cannot be less than 0.015. 0.05%. So, at any locations in this location, right, bonded steel or TMT rebar has to be provided to ensure that. So, that means how do you provide the rebar? The rebar is going to be provided perpendicular to the free edge. So, that means this is the free edge and I have to put rebar like this, right. So, my crack, that means in this regions, if at all I am going to have crack, I am going to have crack like this, right. So, this is the way the reinforcement has to be provided, right. So, where PP is the reinforcement of the pre-stressing steel. So, if you are putting some pre-stressing steel, basically what this code is saying is, you subtract that and then put, but it cannot go anywhere less than 0.05%. Some minimum amount of non-pre-stressed reinforcement or TMT rebars is always required in these edge regions which are not going to be pre-stressed well. So, it may have cracking. So, to avoid the cracking, we need to put some bonded steel, especially in the edge and corner regions, right. So, now we can summarize the discussions that we had in this part. So, in this part of the module, we explained the analysis and design considerations for the two-way PT slabs. We learnt about hyperstatic actions and different load combination that we need to use both in the service stage and ultimate stage, and what are the different types of tendon profile that we need to consider. And we also discussed the stress checks and considerations for the edge and corner panels. So, with that we are completing the part 2. In the next part, we are going to talk about the equivalent frame method, and which is a very important method for designing the PT flat plate or flat slab. So, let us talk about the features of the equivalent frame method in the next part. In the subsequent parts in the next week, we will go through a complete example problem of the design of a PT slab in a building, and we will also check how the results are comparing with the commercial software package which is safe. Okay, thank you.